So last time we spent some time talking about frames of reference. So I guess as usual we'll continue with kind of a recapitulation of a summary of what we talked about last time. And I suppose the new two topics for today lead on partly from the ideas of these reference frames to defining streamline accelerations, kind of the same idea as the accelerations we defined in this moving coordinate system. And then what will take us up for the remainder of this week and the next 2 weeks is using what's referred to as Reynolds transport theorem. And so it's just a fancy way and kind of the general way of being able to do conservation equations. And the three conservation equations that we'll deal with first is conservation of mass. Mass in equals mass out, and the difference between those is accumulation. Conservation of momentum, which is really what Bernoulli is. And then conservation of energy, which is what Bernoulli is if you have frictional loss terms and other energy inputs or outputs to a system. And so that's kind of where we're going with this. And so maybe just without any further ado, just make the point of what we wanted to do and just recapping exactly what we talked about last time. And that is in terms of reference frames. And so one way I thought of one way of making the point about these reference frames is that we talked about this material derivative or the substantial derivative. And the best example I could think of that echoes that is probably the idea of going up in an elevator where you measure, for instance, the velocity in the z direction as a function of z. And if you can imagine that you get on the elevator at the ground floor, and I suppose it would do something like this in terms of a velocity trace and decelerate. So this is the floor where you want to get off. And this would be some initial velocity when you get onto it. And this would be the riding velocity as it goes up. Then we're talking really about accelerations. I guess I want this. So I'm getting good with these colors to make the point this. So this is z0 and this is z1. Then this term, which the substantial derivative is, for at least the component in the vertical direction, is equal to the change in velocity with time of that profile plus vz times dvz dz. So in other words, this term here is a substantial derivative. It's equal to a time rate of change with time component. We can just put velocity in here, and then this other part are these changes with x, y, and z. We only have one component. And so in this part here is is the static observation. So this part here would be, I suppose this could be v1 minus v0 over 2, say. So the average velocity would be this amount. And this part would be v1 minus v0 divided by z1 minus z0. So in other words, this term here, if I draw it, I guess right here, this is just dz, and this is dv. So this is for a static observer. This is what you see. You see someone get on the elevator, it takes off, it goes up, and this is the velocities that you see it go through. It's not changing with time, so if instead of you think of this being as a discrete elevator going up, you could think of this as water coming in here, accelerating to this velocity, going up through the system, then decelerating. So it's continuous. And then this is the convective acceleration that comes from that, and it's all relative to this static frame. If you go up in the elevator, this is what you feel. So if you actually mount this elevator and you go up, you would go from V1, well, the change in velocity would be this, and it would happen over a time frame that this would be at t0, and this would be at t1. So this would just be t1 minus t0. So these should be exactly the same as each other. This other term here is 0 because it's not changing with time. And that's all it is. It's nothing more than that. What we talked about is nothing more than that. It's a way of being able to calculate what acceleration you'd feel, which if you're on the elevator and you had a stopwatch, you'd be able to figure it out. But if you're not on the elevator and you're watching someone in the elevator, you could calculate it just as easily. So it's, the analysis is being able to move between those two reference frames, nothing more than that. And so that is basically what a substantial or a material derivative is. It allows you to be able to calculate what this is. And that's important because really, if we want the forces that are applied on system, it's really this. And so that's, we need an irrefutable way, a single way of being able to calculate. There can only be one set of forces applied on you as you go up in the elevator, and so they have to match in some way. So if you have an internal reference frame, so this is moving, this is on the elevator, this part here, and this is the substantial derivative, and this is the part here that is for a static external static view. And this is moving. And some would call this Lagrangian after Lagrange, and some would call this Eulerian after Euler, frames of reference, but we don't need to worry about that here. So that's it. So that's kind of in a nutshell what that is. So we won't go back to talk about that, but we will. So we'd like to be able to say something about rates of change in different coordinate systems. So acceleration clearly is something we have to know. Acceleration are the forces we have to apply to move fluid through a system. We talked about using Bernoulli's equation, and so it's feasible that we might want to know what the accelerations are relative to Bernoulli's equation. And so let's spend a little bit of time just talking about where this equation might come from. So how do we get the accelerations from Bernoulli? And so one way to do that, I put a note, is page 100, and I guess this isn't done by pages. So I'm going to go back to 6.1, and I'm going to do it on this page. So, oh no, it's not that actually, it's 4.3. I'm trying to give you whiplash. The other PDF thing I used to use had a page number on the top to go straight to a page, but we don't have it. So we might, for instance, be interested in figuring out exactly what the acceleration along streamline is, for the same reasons as we've talked about accelerations in Cartesian coordinates. And so we know that Bernoulli's equation we can write in differential form along a streamline, and also differential form normal to streamline. We know that this is equal to, force is equal to mass times acceleration. And the parts that relate to forces are this part and this part. And the part that relates to the acceleration is the v squared term. And so these are written not very conveniently. Actually, this one's written conveniently, but I'll write them slightly differently. So I'm going to take these two expressions, and I'm just going to write them. I guess I'll write them down below, but I'm going to reorder them. I'm going to reorder them so that they're written first as change in pressure with distance along a streamline. So I'm going to take this term. I'm going to take this term plus the unit weight times The change, I'm writing as partials, it doesn't matter if they're full differentials, is ds. And then there's the inertial term, which is a half density times rate of change of v squared, again along the streamline, and this is all equal to 0. And so I wanted to write it this way, just reordering it, because I'm going to go down through here, and I'm going to write F minus ma is equal to 0. So these are the terms that relate to force. These terms are parallel to a streamline, in terms of my terminology. And I'm going to do the same here. And I'm going to take the part that relates to this component normal to the streamline. And I'm going to write the parts, I should do it in the same order, so I guess this would be the pressure term, right? dp dn. And the part which is the elevation head term is dz dn. They're the same actually, right? And the part which is the centripetal acceleration term rather than convective acceleration term, which is going to be density times velocity squared over the radius, which is also equal to 0. And so specifically, this is the part which is perpendicular to the streamline. So we're using that. So I've just transcribed these equations that we've known down here. And the reason for doing that is that if we want to be able to define the acceleration along a streamline, then what we can do is we can take the acceleration terms, which have to be this term, right? It's going to have to be the components of this term because acceleration is in part of this. So let's figure out what the units are for this. What are the units of this expression here? Pressure is equal to force over area. And it changes along the streamline, so that's length. So this is equal to force over volume. Right? So by definition, this is force over volume. And so what we could do is we could multiply this by or divide through by volume, both sides. And then that would be in the same units as this. And we could also divide both of these expressions through. So this is force per volume. So all of these terms have to be the same. And we could also divide through by just dividing through by 1 over density. Because if we divide this through by 1 over density, then density is in units of kilograms per volume. And so mass divided by kilograms is no unit at all. Volume divided by volume is no unit at all. So by definition, if we divide this expression now through by density, then it's going to be units of acceleration. So if we divide this through by density, divide this through by density, should probably have used a different color, then by definition, these terms have to be accelerations. And I'm just doing that because it avoids 2 pages of derivations that we don't need to do. And we can get straight to a result. And the basic result is that if you look at flow along a streamline, let me draw a picture of what I want to draw. So we have a streamline that looks like this. So by definition, in our coordinate system, this is our vector of a streamline. This is the normal vector, which is perpendicular to that. We have a coordinate system which is, let's call it x and y instead of, I guess it could be x and z instead. And so what we can do is we can define that the acceleration along a streamline is equal to an expression that we saw on a previous page. So let me just change that. Acceleration, rather, is equal to the acceleration along a streamline multiplied by the vector s plus the acceleration normal to the streamline multiplied by the vector n. And so in this, so we know that along a streamline, for instance, there can only be one velocity, right? In Bernoulli's equation, we work with a streamline velocity. It's along the streamline, perpendicular to that, the velocity is 0 by definition, because it's the peak velocity, because it's a streamline. And so the normal velocity is 0, but doesn't mean there's not an effective acceleration. And so we can get the acceleration along this as a function of this. So the acceleration along a streamline is going to be this term here. These cancel out. So this is going to be a half multiplied by the rate of change of v squared with respect to the streamline length, partial or otherwise, multiplied by this vector s. And the centripetal acceleration is the other one, which is going to be normal to the streamline. Again, these drop out, and it's just v squared over r multiplied, well, it's not a dot product, multiplied by the vector n. And so that gives us an acceleration along the streamline. This is a vector. I guess I should make that clear. And these are vectors. So if we wanted to do that here, so what else do we need to know? I suppose, let me do this. The other thing we need to know is that this would be the curvature. So this could be an arc. I didn't really draw it as an arc, but it could be an arc with some radius. And that would be this radius here. This would be the velocity along the streamline, which is a single value, and it's a scalar. It's a speed, if you like. It's got direction along the streamline, but it's along the streamline. So this is just the scalar value of the speed that we have. So if you know what the scalar value of the speed is, you can calculate what the acceleration is from this term here. And I guess we could also write this out slightly differently. We could write this, well, let's not complicate matters. I mean, this, you know that this term here is also equal to v s dvs ds. Right? It's just another way of writing the convective acceleration. And so this whole term here, including the half, could be substituted by this if you want to. But maybe that's some extra information you don't need. I'm going to take that off just because you don't need it. And so what is physically, if we wanted to calculate what this acceleration was, acceleration has components in x, y, and z. And so what these vectors are just the vectors of the coordinate systems relative to the x, y, z coordinate system. And so the easiest way to deal with that is if you wanted to look at, for instance, this coordinate system here. So this is this vector s. You could think of this as being unit length 1 here and unit length 1 here, and then this would be square root 2, right? If it's 45 degrees. So this is 45 degrees. But this is actually a unit vector. So it's a unit vector so that the sum of the squares of the individual components have to add up to 1, which means that this length here has to be 1. So what we could do is we could just divide this vector through by, if it's 45 degrees, just divide this through by square root 2. That means that this gets divided through by square root 2, and this gets divided through by square root 2. And then this is 1 by definition. And so then this acceleration term, if you write it out in its full components, is that it's equal to a half dvs squared, which we can calculate ds, and there's going to be a vector. The component of s, which is this term here, what is s? In the x direction, it's going to be 1 over square root 2. So it's going to be positive. So there's going to be a length here, which is this amount here, which is plus 1. There's going to be a length in the y direction, which is going to be this length here, which is also plus 1 divided by square root 2. And there's no component in the z direction, which is in the page, which is 0. And so for the other term, it's going to be the streamline velocity squared divided by the radius. So this is just a scalar value, and multiplied by this vector n. So what's n? N is going to be the same. It's going to be, so if this is 1 unit long, as the s one has to be, then the x component of the vector is going to be this, which is minus, it's going to be 1 over square root 2 again. This is going to be minus 1 in the x direction. It's going to be plus 1 in the y direction. And into the page at 0. That's all it is. So it's just a way of being able to do that. So we could have gone through a nice long derivation, but we have these defined as convective accelerations from Bernoulli. So all we did was manipulate this to get it in the right unit so that these were actually accelerations by dividing through by densities. And once we had these accelerations, we just multiplied those accelerations by their orientations to get the magnitudes in Cartesian coordinates. And so in this then, this would give us the acceleration in x, the acceleration in y, and the acceleration in z, which is all this is. So that's what all that expression is. So in other words, from our previous stuff last time, we talked about getting accelerations into x, y, and z from velocities in those directions. Here we can also get accelerations in x, y, and z if we know what the streamline velocity is. Yes?
In what situations would we have a z component?
In what situations would we have to?
A z component to the acceleration.
In this case, it's into the page, and so if we had it, it would just be a number that would be in here, that would be non-zero. I'm not sure if I'm answering your question. I'll ask you the question again if I didn't answer it. Okay. So, I mean, in general, you could have a component in the z direction. And so there's no reason that you can't write Bernoulli in 3 dimensions. Okay. All right. So that concludes our work, I guess, on looking at accelerations. Okay. And of also looking at the important difference in reference frames. So let's see, where are we? I'm not sure where we're back to. I wish I could just skip to, well, we're much further. There it is. All right, let's come back to this. So we didn't talk about this last time, but let's talk about it now. So the other thing that we'd like to do is we'd like to talk about conservation equations. So the whole discussion on substantial derivatives and material derivatives and moving coordinate frames is related to the idea of control volumes. We talked about the fireboat New York harbor moving across the harbor, and it matters whether we're standing on the boat or standing off the boat as to what the velocities are that come out of that gun. Of course, it's the same velocity that's coming out, but it appears different to us. So what we can define, we can define control volumes, which are 3 main types. One would be a fixed control volume that doesn't deform, and so that an example of that would be a pipe that would have water flowing through it and just sits there. Water comes in one side, goes out the other side. probably doesn't accumulate in this particular case. One that is static but could be moving. And so the classic example of that could be a jet engine, that physically it moves through space. Air comes in through the input, gets combusted with fuel and goes out through the exit. And physically it translates, but it doesn't deform. It always stays the same size. And the third one is one that moves and also deforms. And so the classic example of that would be blowing up a balloon and just letting it go and letting it zip through the air. It loses mass as it kicks it out through the bottom, and it also moves in space. And so those are the three kinds of systems that we can think about when we look at control volumes. And so one way we can think about this, and I guess I showed this, let's show it again. We're looking at this thing a little earlier on today. The idea of defining a control volume in terms of, even the most simplest system is filling a bucket up, filling a beaker in this case. And so you can imagine that if you wanted to calculate how long it takes to fill a beaker, you calculate the volume of the beaker, you divide by the volume rate, and that gives you the time it takes to fill, so you know how to do that. But there are some more. You'd be surprised how complicated we can make this to be able to satisfy these three conditions of a static system, a moving system, and a moving and deforming system in terms of the control volumes that we might want to apply for this. And so actually there's some interesting lessons here, right, as well. So we know that from Bernoulli's equation, if we want to close it when we only have 4 variables, one thing we can do is continuity. We can write the volume in upstream multiplied by the area, or the velocity in times the area times the area downstream. They have to balance. And so we know in this case that this should be the equation of a free jet. So the velocity of this should be square root 2gh coming down through this. And because it's accelerating by gravity, we can see some of that here. The area here is much larger than the area here. So by definition, it has to be traveling much faster here because it's not accumulating fluid. So that's an aside. But if we wanted to be able to analyze this control volume, we could do it in any of these 3 ways that we've looked at here. And I was going to try, so I made a screen capture of this, and I'll try and explain exactly what I mean. So there's these three distinct ways that we could try and analyze this. So what we could do is we could take the static control volume. So we could make a control volume that looks like this. And I know you can't draw this, but now what we have is we have the jet that's coming in here. And to be able to analyze that, this is a static control volume. It's not going to change in size. So what we'd have to do is we'd have to allow for the fact that fluid is coming in through here, but also, ultimately, fluid is going up through the area that is outside this jet, right? This is the jet that's coming down. Perhaps I should do that a bit darker. So this would be the idea of a static, non-deforming control volume. The other way we could do it is we work through this. So we have so that would be just the idea of a static control volume. The other one was a moving, non-deforming control volume. So I guess that would be something that would look like this. So at time 0, it would look like this. Let me make it bigger. And we want it to be non-deforming, but it can be moving. So at time, some extra time, if we allow this control volume, for instance, to follow the surface of the water as it goes up, so that the green box is exactly the same size as the red box, but it's translated, then we have, for instance, the fluid coming in through this part here, which would be going in. The fluid velocity on this, if it was tagged to the top of the fluid as it rises, would be 0. But there would be fluid going out of the bottom because this whole green surface would be moving up, and it would be moving up at the velocity that this surface was rising. So we can, if we wanted to make life complicated for ourselves, represent this by a non-deforming control volume, but one that translates in space. So that would be the second of our options, the jet engine, if you like. And the third one, if you want to get, oops, this one can go out. There. And so the third one would be moving and deforming. And so I guess at time 0, this would look like this, if we're taking this as 0. And at time after that, it's moving and deforming, so it would be this. It's getting bigger. So in this case, again, the idea is that on this part here, fluid would be coming in here. There would be no fluid going across here because this would be rising with the velocity at which the water level is rising in the beaker. There'd be nothing going across here, but we could use that as a mechanism to do that. And so the idea is that even a very simple system like this, filling a bucket, we could represent it in each of those methods. Okay. It may seem esoteric at this moment, but we'll ultimately solve this problem using these concepts. It's relatively straightforward. Okay? So, that's where we'll ultimately go. So this was what we didn't talk about last time. Just to make you feel good, this is all the derivations we didn't do today to get the convective acceleration, by the way. And this is the equation that we're now going to concentrate on, which is Reynolds transport theorem. This. Looks kind of complicated, but let's try and explain it in a way that at least hopefully makes some sense. So this is the idea. It's large. Okay. So Reynolds transport theorem is something that is really, although it looks kind of complicated, it's quite simple. In the case of conservation equations, it says that influx of that quantity in equals the efflux of that quantity out. The difference between the influx of that quantity in minus the amount going out is accumulation of that quantity. And that quantity could be mass, as we'll talk about now, mass of fluid, or it could be momentum, or it could be kinetic energy. And so the reasons that we wanted to talk about substantial derivatives are really because this turns up in this. This is taken out of the book. I think the book does a reasonably good job of trying to explain this, I think. And hopefully I can emulate that. But these are basically the terms. They look complicated because they're integrals, but that's integrals aren't anything particularly special. But Reynolds transport theorem says that for the three systems that we are dealing with, in this equation, we can substitute values for this extensive property, uppercase B, which would be either mass, momentum, or energy. The three things we'll talk about this week, next week, and the following week. So, for instance, we could substitute, since we're talking about mass, for mass here. And there's an intensive property here. And this intensive property is this extensive property per unit mass. And so, in this particular case, since we're dealing with mass, which is B, this would be mass. And this intensive property, B for our case here, would be just 1. But the reason that we talk about Reynolds transport theorem is because we can apply it to conservation momentum and conservation of energy, and we will. And it's important to apply to those because it defines the forces that are applied on structures with fluids flowing through them, basically. And so this is what Reynolds transport theorem will look like for our system. This term for us will always be 0 because it's taken relative to the big, wider world. So in other words, if you have some people going on an elevator in a hotel, then the amount of people that go on the elevator we calculate in this, and the ones that leave the elevator we calculate from this. But this property includes all the people inside the hotel and inside the city and inside the country. So the reference frame is the whole universe, if you like. And so there is no net mass change within the universe. So this term is always going to be 0 for this system we look at. So this will be equal to 0. And these two represent components. This is mass rate in minus mass rate out equals accumulation. Actually, it's should be backwards, I guess. Just mass rate in minus mass rate out equals 0. That's all it's saying. But it happens to be just an integral. And so these terms here refer to the fact that this behavior is written on a control volume. And this represents the bucket that we have, that we're putting stuff into. This is this control volume that has a density and a volume in it. And this represents a control surface. And it can accommodate all of these conditions that we talked about in terms of stationary control surface, a moving control surface, or a moving and deforming control surface. And we can deal with that. So maybe let's try and explain it if I shoot this down a little bit so we can see this. And so this is the basic idea. Yeah, let me do something else. Let me move to this, just because I want to draw some things. So I'm just going to write this out so you can keep up with me. And so this is wherever we are, we're 6.2. Osborne-Reynolds transport theorem. And we're doing it for conservation of mass. What's the best way to, well, let's write it out first. So we have that 0 is equal to an integral density, volume, a rate of change with time, plus another integral. This is over a control volume. This is over a control surface. And it's a density multiplied by a velocity dot product with n. And what do we use? dA. So that's the expression. If you look at these terms, and if you do this integration, and so in terms of, let's draw a simple shape. And the simple shape would be something, would be a box. And we could have a velocity 1, the velocity 2, and we could seal the sides so there's nothing going in, and we could probably define these terms. So this has some volume V, and this whole dashed line that I'm defining here is the control volume. Which is this, is included in that. And the control surface, I guess, would be it overprints that. So I guess the control surface is just the contour, and the control volume is everything inside the contour. So this is control surface. And so just to explain what these terms are, if, for instance, we took this is the accumulation. So if, for instance, the density was constant, and we did this integration, then this term here, if I just move it down here, you could also write as the rate of change with time of density and volume. So I'm just doing this integration over the volume, and so if you integrate this over V and the density is constant, then you get this expression. So that's one way you might think about writing it. The other component, which is this is the mass in minus mass, actually mass rate out. We could calculate by knowing what the velocity is. So in other words, if you multiply the density times the velocity times an area, so you know what Bernoulli looks like, right? Velocity 2, area 2, and fluid of density rho. Then the mass flow rate out of this is equal to the velocity times the area times the density, right? So velocity times area is length over time times length squared, length cubed over time. And length cubed over time times kilograms per length cubed is kilograms per second. So the units of this have to be kilograms per second. So it's a mass rate. So we use this mass m with an overscripted dot. Overscripted dot is ddt, right? Rate of change. And so that's kind of what this is, right? Here's the density, here is a velocity, and here is an area. It just happens to be written as an integral, and it happens to have this term here, which is just the dot product. And all this dot product is it's saying that we want a unique value of velocity that's going across that boundary. And the only way we can get a unique value of that velocity, if, for instance, you have a boundary that looks like this, and you have a fluid that's going across it at some streamline velocity, the only way you can get a unique value that's represented to this boundary is to figure out exactly what the component normal to the boundary is. And this is this normal component. And if you multiply this normal component by dA, which is this length here, so dA times Vn is going to be a volumetric flow rate. If you integrate this integral doesn't make any difference. So this is a meters cubed per second. And if you multiply it by density in terms of kilograms per meter cubed, then you have kilograms per second. So my point is that this integral is really just a mass flow rate out of the system. And the reason for using this dot product is it gives you the magnitude of the flow rate across that surface, but the normal to the boundary surface. That's all the dot product gives you. Yes?
Is the change in area meant to be from the bottom of PS to
It's just a segment that this is flowing over. So it would be the whole, it's a component of the area. The integral just means that you're doing it over the whole thing. Okay. So perhaps not boundary. So that's really all this is. And so The only important thing that you need to remember is that when you look at dot products, if this is your boundary and your fluid is flowing in this direction and your normal to the boundary vector is aligned with it, then V dot N is positive. If this is the outside, if this is the flow and this is going across this side of the boundary, then the product, it's just the cosines of this angle. So the normal to the boundary direction and the flow rate are aligned, and so the dot product is equal to 1. And the opposite is true if, for instance, the velocity was in the opposite direction and it was flowing into the system and your normal is in the opposite direction, then V dot N is the negative value of the velocity. And so my reason for doing that is that you might choose to write this expression here, which is Reynolds transport theorem, as I've already started doing down here. The left-hand side is 0. This is the accumulation term. And this is the other term, which is just a mass flow rate. And the sign convention is if it's out, then m dot is positive because of this. And if it's mass flow rate in, then m dot is negative. Right? So in this case, the exposition of that is here. This is the outward normal vector to the system. The flow velocity is here. They're in the opposite direction. So the direction cosine of the dot product is minus cosine 180, it's 180 degrees, I guess. Yeah, minus cosine 0. And so this would be negative mass flow rate, and this would be a positive mass flow rate. And so you just need to be able to be aware of this sign convention to do that. So the other thing which is worthwhile doing is that probably this isn't quite sufficient for what we need. But the other thing that we can do in this expression is we can also split this up into by differentiating by parts. So if we differentiate this by parts, we end up with this. And this is probably the most useful expression you'll have on this. So this is density multiplied by change in volume with time plus volume multiplied by a change in density with time. So that's this expression here split into two parts plus m dot. So if you like, if you feel more comfortable with it, this is the other way to write Reynolds transport theorem. And for most cases in everything we do in this class, this will probably suffice. You just have to remember this sign convention, which will be beaten into you. So that allows us to solve lots of physical problems. Maybe we have a chance to, there are a couple, everyone okay with that? I mean, this is quite fundamental. So you just have to think about what these individual terms are. I won't go through it, but you can perhaps think about what we've said. This form of Reynolds transport theorem will be perfectly adequate for everything we do in this class. You just have to remember the sign convention, and that is that if m is positive for out and negative for in, and so when I say positive, it would be V2 A2 rho in this particular example here. Right? This is going out. And it would be minus V1 A1 rho for the mass rate in. And in this case, if volume is increasing, that is positive. And if density is increasing, that is also positive. So that's the sign convention you have to remember. So if density is changing with time, that's a positive rate of change. If volume is changing with time, that's a positive rate of change. Okay? So let's just try and see if we can apply that very quickly. So we've done this, blah, blah, blah. So here's a system. So there are a couple of relatively straightforward examples trying to make the case. So let me use black. So you have a system that looks like this. This is what Reynolds transport theorem looks like. This is what the idea of a dot product is that gives us this positive or negative flow rate. We can write it in this slightly more straightforward way, like we have here. And then we can try and analyze the system. So this is exactly the expression that we ended up with on the other page. So how would we solve a problem using this? So, simple idea. A non-deforming control volume. We pump gas into a system, into a compressor. We have it stoppered off, so nothing's going out. And we look at the individual components in this equation. The control volume is not changing size during what we're doing. And so the dV dt by definition has to be 0. It's flowing in at some velocity, but it's not flowing out at some velocity. And so by definition, the density has to be increasing, right? Mass is going in, the volume's not changing, so we have to be increasing the density of the stuff that's in there. And so this term has to be something that's real and changing. And we have to use the calculation for the mass flow rate. It's going in at velocity. What's the mass flow rate? M1 is equal to the velocity it goes in at, its density, and its area. It's going in, but the outward normal is out, so it's negative. So that's a negative value of this. That's here. So this mass flow rate is this. We have this expression here. If we do it over a certain period of time, then we can just rearrange this equation to get it as an equality. If we do that, we end up with this. We multiply both sides through by dt. We integrate between when we start pumping in and sometime later on. And if we do that, then we can just solve this equation where we'd like to know what the final density is of our system based on the initial density that we pump it in at and the velocity at which we're pumping in at. We can solve for this. If we wanted, for instance, just to know the rate at which density was changing, then we can solve that straight away here by just solving this equation. We don't have to integrate it. But we know that this is going to be a positive quantity because this will go to the other side. So in other words, if we're flowing net fluid in, mass has to be increasing. That's in this here, so the density has to be increasing. So so this is the case of a non-deforming control volume where the density is changing. It's absolutely taken account of in our Reynolds transport theorem. Let's just finish the second one off because it gives an alternative way of looking at a deforming control volume. So here the control volume will look something like this. So we're flowing water, maybe it's into a cistern and a toilet or something, right? Doesn't that come in through the bottom? I guess it comes in through the top. So this is the converse. So the water's coming in, the water's incompressible, it's not being subject to a change in pressure. This is the conservation of mass equation. The density is not changing as it comes in, so this by definition is 0. But the volume of this control volume is going to change as time goes on because we're going to let it move up with this surface as it rises up through the system. So we're going to allow that to happen here. And we're going to calculate what the mass flow rate is in. The mass flow rate is the density it comes in, the velocity it comes in, times the area it comes in. It's into the system, so by definition it has to be negative. And so this equality becomes this. And we have another simple equation. And so for instance, if we wanted to know exactly what the rate of change of the volume of this control volume was, we could calculate that straight away just from knowing this. We know the velocity, we know the area, we know the density, and we can calculate that. That's our only unknown. If we wanted to know what the volume was at any particular time, we can just integrate the volume rate of change. We could integrate this, and that's what we're doing down here. And we can calculate where the height of the top of this cylinder would be at any particular time. And so that's what we do. So Reynolds transport theorem, we've talked about substantial derivatives because that comes in on the left-hand side, which already we've said is 0. We can basically write Reynolds transport theorem saying mass rate in minus mass rate out equals accumulation. It ends up being a term that looks exactly like this. Bless you. And we can use this creatively to solve some problems related to conservation of mass within systems.